All right, section 10.2. I'm actually glad I didn't record my psychological advice that would be on YouTube for our psychology professors on campus to actually review and tell me how wrong I am about everything that I just told you. But it sounded good to me whenever I read it. It sounded like me, at least. All right. So, consider the parametric equation. X equals a function of t, y equals a function of t. Remember, you don't graph t typically, although you can. Remember our applet that you used for the tech homework? You can actually see what happens with x on one graph, what happens with y, but then we combine them together and see just what happens with x and y together without graphing t, other than to think of t as time. So let's assume that we just look at the curve as a static thing, not being drawn out over time, but at a static curve being drawn. Let's say our curve goes from, say, a t-value A to t-value B. When we look at it, we think of it as y is some relationship to x, okay? It's a differentiable function of x. So when we have a curve, you don't have to draw this, and you have a point right here, if this is y equals f, capital F of x, right? The slope of that is dy dx, right? That's the slope. That's what we learned the derivative to mean, is the change of y with respect to x as the length of your x, as your delta x goes to 0. So that's where we get this slope. So what we're really looking for is dy dx, but what we actually have is y is some function of something that's a function of t. Right? Since, and that should be f, little f, sorry, not g. Fix that. Right? Because of that right there, x is a function of t. So y, typically, this whole thing right here is g, right? Capital F of little f is going to then be g, because if we think of y as a function of x and then plug in x as a function of t, now y is a function of t. If you use the chain rule, in fact, that's what goes right here, then dy dt would be capital F prime of f of t times f prime, I said t, wrote x, t, times little f prime of t. Remember, you take the derivative of the outside, leave the inside alone, times the derivative of what's inside. Okay? Now, this is dy dx, because this right here is x. And this right here is dx dt. So that's where I get this equation right here. dy dt is dy dx dx dt. That's one of the nice symmetries of the differential notation that Leibniz gave us, the d notation for derivatives. Because if you look at this, it almost looks like if you think of these as fractions, the dx's are canceling, and that's obviously true, right? dy dt is dx dt, sorry, dy dx dx dt. Cancel the dx's and you see that that's dy dt. But technically those aren't fractions, they are symbols for the derivative. But once you have it written in this form, this is what we really care about. This is the slope that we want. So if we solve for dy dx, which represents the slope of the tangent, then we get what we really want. I'm just going to divide the dx dt to the other side so that the slope of the tangent, dy dx, is dy dt divided by dx dt. Or dy dx is g prime of t over f prime of t. This is what I remember, but either one of these will work as long as you keep track of which one is the y function, which one is the x function. So you take the derivative of y with respect to t over the derivative of x with respect to t, and that will give you the slope of the tangent line. dy dx is dy dt over dx dt. And again, if you think of these as fractions, if you were to invert and multiply the denominator times the numerator, so dy dt times now dt over dx, the dt's cancel and you get dy dx, so it actually makes perfect sense. But that's the formula you'll now use if you're asked to find the tangent or the slope of the tangent for a parametric curve, then you have to do it by dy dt over dx dt. All right, so real quick, let's take a look at this parametric curve. X equals t squared and t cubed minus 3t. Now, real quick, I'm going to jump over to Wolfram Alpha, and I'm going to graph that for you. You don't have to do this yourself, but I just want to graph it so we see what we're looking at. And we'll draw a rough sketch of it by hand. It is parametric plot, and then we did t squared, comma, what was the other one? 3?
T cubed.
Oh, just t cubed minus 3t?
Yes.
Okay, so here's the shape of that curve. And notice where it goes up to a height of about 2 and down to negative 2 in the loop, but it crosses itself, something that a function can't do, but a parametric curve certainly can. That makes this the interesting point I want to look at. What is the slope of the tangent at the point 3, 0? And what do you notice? There's two. There's two tangents there, so we're going to find both of them. Okay? Let's do that. So the graph of the curve, I'm just going to come off to the side here, go up 2, down 2, over 3. The curve does something like that. Right? It goes off this way, goes down that way. And so we want to look at this point right there. That's the point 3, 0. First of all, let's algebraically or analytically show that there are two tangents at that point. Now, when I say there are two tangents at that point, what I mean is let's show that the parametric curve is at that point for two different values of t. Okay? Now, what I mean there is the x function has to equal 3, and the y function has to equal 0. So you have t squared equals 0 and t cubed minus 3t. Oh, I had that backwards. T squared equals 3. And t cubed minus 3t equals 0. So we need to find the values of t that solve both of those at the same time. And so what you do is you solve one, and you take all of the answers and plug them into the other, and the ones that satisfy both are your t's. Anything that doesn't satisfy both is not. So the easiest one to solve here is this one, right? What does t then equal? Careful, not just square root of 3. Plus or minus. So there's actually two of them. Okay? And then we check. Do both of them satisfy this? So try t equals square root of 3. That's square root of 3 cubed minus 3 times the square root of 3. And that works. That gives me 0 because square root of 3 cubed is a square root of 3 times square root of 3 times square root of 3, which is 3 square roots of 3. And you subtract 3 square roots of 3, you get 0. Check. So t equals square root of 3 is one of those values. In other words, if I plug in square root of 3 into this parametric curve, that's the time at which it passes through that point. But let's also try t equals negative square root of 3. So negative root 3 cubed minus 3 times negative root 3. I'm just plugging it into the second equation to make sure that it satisfies it. It's very possible that they don't all satisfy it. In this case, it actually does, because that gives me negative 3 root 3 plus 3 root 3, which is 0. So t equals negative square root of 3. there are 2 times at which it ends up at that same point 30. So to find the slopes of those tangents, we're going to find dy dx from this formula here, plug in square root of 3 for t, and then we're going to also plug in negative square root of 3 for t, and that'll give us 2 different slopes, the positive one and the negative one. Okay? So what is dy dx? Well, remember that's dy dt over dx dt. Slope of the tangent is dy dx. We find that by taking the derivative of the y over the derivative of the x. So derivative of the y, 3t squared minus 3, just taking the derivative of this, and 2t on the bottom. So I'm going to write it this way, dy dx evaluated at t equals, let's do square root of 3 first, the first one we got up here. I'm going to plug in t equals square root of 3 into these guys, so I get 3 square root of 3 squared minus 3 over 2 square roots of 3. Square root of 3 squared is 3. 3 times 3 is 9 minus 3 over 2 square roots of 3. Which is 6 over 2 square roots of 3. 2 goes into 6 3 times, and then 3 divided by the square root of 3 is the square root of 3. So that's the slope at time t equals square root of 3. So that would be the positive slope right there. And to do dy dx at t equals negative root 3, we plug negative root 3 into the same formula for dy dx. 3 times negative root 3 squared minus 3 over 2 times negative root 3. Yep, so the top is still 6. The bottom will be negative 2 root 3. Two goes into 6 3 times. 3 divided by root 3 is still root 3, but now you've got the minus sign. So there's your slope at t equals negative root 3. That's this negative slope direction here. But now you can find slopes of tangents. All it is finding what value of t gives you that point. That's what I did up here by setting those equal to. So if I gave you the xy, you still have to find the t. Right? I gave you 3, 0. You got to find what time gives me that, because t is what you have to plug into your derivative. Okay? So that's first derivatives. First derivatives tell you slope. What do second derivatives tell you about a function's shape? Kind of. It's a different C word. Concavity. Concave up or concave down. Curvature is a thing, but you don't know what it is yet. We talk about curvature in Cal 3. Circles have constant curvature all the way around, but the larger the circle, the lower the curvature. The smaller the circle, the higher the curvature. We'll define what curvature means in terms of partial derivatives next year, next fall. But for second derivatives, that tells you concave up or concave down, right? Concave up or concave down. Is the second derivative. So if we want to find the second derivative with respect to x, then it's d dx of dy dx. It's the derivative of the derivative with respect to x with respect to x. Okay? Now, it's actually not that hard to see what's going on here and how we actually get the formula. If we realize this right here now is a function of t, right? dy dx, even though it's got y's and x's in the notation, remember what we got up here when we actually did it? We get a function of t out of it, right? So what I'm really doing is I'm doing a derivative with respect to x of something that depends on t. And x also depends on t. All right, so what I'm going to do, I'm going to scroll back up. I'm going to look at this formula right here. So instead of having that y here, and you don't have to draw on yours, but I'll do this with highlights. Hey, give me my, what's going on? This y here matches this y here. So what I'm going to do is instead of having dy dx equals dy dt over dx dt, it's going to be d whatever, in this case the derivative, equals d whatever dt over dx dt. And the whatever is now my dy dx. My dy dx. Okay? So here's what you do in practice. You find dy dx, and then to get the second derivative with respect to x, you still put dx dt down here in the denominator, but on top you take the derivative with respect to t of the dy dx that you just got. Okay? So in the previous example, I'm asking you to determine where it's concave up. So the question is essentially, where is the second derivative positive? That's concave up. If it's concave down, it's where is it negative. But to first do that, let's find the second derivative. So I'm going to use this formula right here. The second derivative with respect to x of y is the derivative with respect to t of dy dx over the derivative of x with respect to t. So first of all, remember, what's dy dx? On the previous example, it was 3t squared minus 3 over 2t. Now you can either use the quotient rule of this on top, or you can actually split this up into two fractions. To me, that's easier. It's less messy than low d high minus high d low over low low. I could rewrite this as 3t squared over 2t, which actually turns into just 3t over 2 minus 3 over 2t. Which that's, just to write it a slightly different way, that's 3 halves t minus 3 halves t to the minus 1. So just a little bit of algebraic reformulation makes it a lot easier to take the derivative, right? So what's the derivative of that? Derivative of 3 halves t is 3 halves. The derivative of minus 3 halves t to the minus 1, the minus comes out front and makes that plus 3 halves t to the minus 2, which I'm just going to put the 2 to the minus 2 on bottom. This t to the second in the denominator. So take all that, plug it in here. We've got 3 halves plus 3 over 2t squared on top, And on bottom is still dx dt. So just 2t. Notice, I don't have to take the derivative of the derivative on bottom. I just have to take dx dt on the bottom. 2t. All right, so let's simplify this complex fraction. We don't like fractions inside fractions. Do you know the easiest way to simplify a complex fraction? Multiply by, well, I would multiply by something that cancels all the denominators. 2t squared. The lowest common denominator is 2t squared. If I multiply the top and bottom by 2t squared, then I get, when I multiply times this one, I get a 3t squared. When I multiply times this one, I get just plus 3. And on bottom, I have a 4t to the third. So there's your second derivative. That's your concavity. So question, what values of t make this positive? So 0 for sure. Actually, 0 is a problem, not even 0. I can't plug in 0. When is a fraction positive? When its numerator and denominator are both positive or both negative. Now the top, look at the top for right now. Is that ever negative?
No.
Why not?
Squared.
T squared is always positive. So 3 times the positive is positive. Add a positive. The top's always positive, right? Right. So if I put in a negative t, the top's positive, and then bottom would be negative. So the only things that work are t greater than 0. And that's just me reasoning out, when is this positive? It's when t is greater than 0. Okay? So it's concave up when t is positive. Okay, those are just a couple of application questions, but again, the point of this is you need to be able to take the first derivative, dy dt over dx dt, or the second derivative, which is d dt of the first derivative over dx dt. So those two boxes, this one and this one, are what you need to know for tangents and concavity. Let's talk about areas. If you start with a function y equals f of x, from x equals a to b, right? When you have a curve like this, here's a, here's b. The area underneath there, if y is capital F of x, then there's how we find the area, right? So all I'm going to do now is I'm basically going to use substitution. I'm going to let x equal f of t. Just like I would do, remember whenever we did substitution in trig substitution? We assigned x to be something in a different variable. That's the same idea. Let x equal f of t. Then, well, in fact, I'm going to come down here and write it out in just a second. So I'm going to using substitution. I left out a word, so I'm going to put it in the blank. Substitution in the integral above. So if you have the integral from a to b of capital F of x dx, we're going to let x equal some function of t. So first thing we do is we plug it in, f of t in here. Plug in your substitution. That's the first thing you change is your integrand. Second thing you change is the differential. So what's dx? If x is f of t, f prime of t dt. So that's f prime of t dt here. And then you change your limits. Now, I just gave them to you. I'm telling you that t equals alpha starts this, and t equals beta ends it. So I'm going to go from alpha to beta now. But you've got to find where's the t that corresponds with point A, where's the beta for t that corresponds for point B for x. But then the last thing to notice is this right here is your y. It's your height of your function as a function of t, which means it's g of t, right? That's what y is. We've already replaced x with f of t. So what the actual formula is the area under the curve is the integral from alpha to beta of your y function times the derivative of your f function dt. So if you want to find the area between a curve and the x-axis, so underneath the curve, this is how you do it. You take the integral from alpha to beta, that's your starting parameter to your ending parameter, of your y function times the derivative of your x function dt. So that's how we find areas with parametric curves. So for example, one of the curves we looked at last time, like I told you, was the cycloid. That's where you've got the circle of radius r sitting here, and it's going to roll, and you're tracing out the point on the outside of this thing as it rolls. Do you remember that animation? I showed it to you last time. I can pull it up if I need to. It's not really all that important. This curve is based on the radius, and then theta is how far this thing has rolled. We learned, by the way, from looking at that applet, that little browser tool with the sliders, that this value right here corresponds to theta equals 0, and it traces out, and this was one of the homework problems you did in the tech homework. That corresponded to theta equals 2 pi. It traces out one cycloid from 0 to theta equals 2 pi. So that's like my alpha and my beta. So the area underneath this curve, again, alpha to beta of g of t, or in this case theta, f prime of theta, d theta. So in our case, the integral goes from 0 to 2 pi. And notice, by the way, I'm not using the x value of 2 pi r, that is how far it is on the x-axis. I have to use the value of the parameter that gives me that point, theta equals 2 pi. And now I'm going to do g of theta, that's your y function, r times 1 minus cosine theta, times f prime. What is f prime of theta? The derivative of this with respect to theta.
Would be r minus cosine.
Okay, so actually I'm going to just leave the r out front because it's a parameter, so it's just 1 minus cosine theta. Actually, it turns out to match the y, doesn't it? It's kind of cool. If you'd multiply the r out, you'd have r minus r cosine theta, but you can then pull the r back out. Or you can just use the rule that when you take the derivative and you've got a constant out front, the constant just stays there. And you can take the derivative of what's inside. So 1 minus cosine theta. So this is going to be times f prime, which is r 1 minus cosine theta. It's just a coincidence, by the way, that f prime matches g. But in this case, it does. All right, so here's what I've got then. I've got the integral from 0 to 2 pi r squared times 1 minus cosine theta squared d theta. So how do we integrate this? Let's take the r outside. If I do substitution, I need a sign in there, right? If I use u equals 1 plus cosine theta.
You have to do it by parts.
Well, let's just multiply this out first. Let's do the square. Because when I have just 1 minus cosine squared d theta, I don't have pieces to assign to u and to dv. Basically just got the 1 minus cosine theta squared and a d theta. So if we multiply that out, if we FOIL it, what do you get? All right, 1 minus cosine theta times 1 minus cosine theta.
1 minus 2 cosine theta plus cosine theta.
All right, 1 is easy to integrate. 2 cosine theta, easy to integrate. Cosine squared, I need a identity. Because squares are a pain, but I know that there's an identity somewhere that changes cosine squareds to not cosine squareds. Yeah, I think it's
Should be like 1/2 times 1 minus cosine.
cosine squared theta, I think it's 2. You've got your reference pages. I left my reference pages behind. I need something that turns cosine squareds into not squareds.
Yeah, cosine squared is 1
1/2.
1/2 times 1 plus cosine.
There it is. 1/2 times 1 plus cosine 2 theta. Cosine of 2 theta is easy to integrate because it's not a function times a function. So then, here's what I've got. Integral from 0 to 2 pi of 1 minus 2 cosine theta plus, and I'm going to go ahead and distribute this, 1/2 plus 1/2 cosine of 2 theta d theta. And if you don't mind, I'm going to go ahead and do this. This becomes 3/2 because 1 plus 1/2 is 3/2.
Make sure r squared up.
Oh yeah, up front, r squared. Okay, so I've got an r squared times 3/2 times theta. The integral of 3/2 is 3/2 theta. Integral of cosine is sine, so negative 2 sine theta. Integral of cosine is sine, so I'm going to have a cosine becomes sine. And then when I take the derivative of that, I got to multiply by 2, and I need to end up with a 1/2. So I'm going to use 1/4. Right? The derivative of 1/4 sine of 2 theta is cosine of 2 theta, and you take times 2 times that 1/2. 1/4 gives me 1/2, so that works. 0 to 2 pi. Now, if that was too much in your head, then we can use U substitution and still get the same answer. So now I'm going to plug in 2 pi. I'm going to get r squared times 3/2 times 2 pi. Sine of 2 pi is 0. Sine of 4 pi is 0. And then minus, I plug in 0, I get 0, 0, 0. So really all these are gone. And what I end up with is 2's cancel, 3 pi r squared is the area underneath there. And I'm out of time. I got to stop there. I did not finish arc length, which is the last example. I will finish that on Friday, and we will go ahead and start polar coordinates on Friday as well. Again, don't forget, if you can come at 2, please, please, please come, and we'll see you then.